When German reconnaissance aircraft returned from missions over Britain in late January 1942, their cameras captured something new, taxiing at Royal Air Force stations across Lincolnshire and Yorkshire. Another four-engine bomber, the analysts at Luftwaffe intelligence headquarters in Berlin, barely looked up from their desks. Britain had been churning out heavy bomber designs since 1939, and most of them were frankly rubbish. The Sterling couldn't climb above 15,000 feet without wheezing like an asthmatic pensioner. The Halifax kept shedding tail units mid-flight. And the Manchester? That twin-engine catastrophe was already being withdrawn from service after spending more time in maintenance hangars than over Germany. So when photos of this new aircraft, designated Type 464 in early intelligence reports, landed on German desks, the assessment was brutally dismissive. 4 Rolls-Royce engines, conventional mid-wing design, twin tail fins, nothing revolutionary. Just another British attempt to cobble together a credible strategic bomber from an industry that seemed incapable of matching German or American engineering standards. The wingspan measured 102 feet, putting it squarely in the same category as every other lumbering 4-engine design cluttering RAF airfields. Oberst Josef Schmidt, Chief of Luftwaffe Intelligence, filed the Type 464 reports alongside dozens of other British aircraft that posed minimal strategic threat. The German assessment wasn't entirely unreasonable. Britain's heavy bomber program had been an absolute shambles. For 3 years, the Air Ministry kept issuing contradictory specifications, demanding aircraft that could somehow be both long-range, strategic bombers and tactical support platforms. Manufacturers responded with compromised designs that excelled at nothing. The short Sterling, Britain's first 4-engine heavy bomber, entered service in August 1940, but was already obsolete. Its massive landing gear and short wingspan meant it could barely reach operational altitudes, where German fighters and flak did their worst work. Crews called it a death trap. German intelligence had thoroughly documented these failures. Interrogations of downed RAF aircrew revealed chronic mechanical problems, inadequate defensive armament, and abysmal bomb loads that barely justified the fuel consumed. Getting to target and back. When Luftwaffe analysts compared British heavy bombers to their own Heinkel, He-177, or even to American designs like the B-17 Flying Fortress, the conclusion was obvious. Britain had lost the heavy bomber race before it even started. The Type 464, soon to be designated the Lancaster, arrived at No. 44 Squadron at RAF Waddington in December 1941 for operational trials. German observers noted the squadron code KM appearing on reconnaissance photos throughout January and February 1942, but saw nothing worth elevating to high command. It looked like every other British 4-engine bomber. 4 engines, 7-man crew, dorsal and tail turrets for defence. The only notable difference was those twin tail fins instead of the Halifax's single large rudder. But that was merely a design variation, not a capability revolution. What German intelligence completely failed to grasp, what their rigid assessment criteria couldn't detect from grainy reconnaissance photographs, was the revolutionary space between those wings. While analysts catalogued engine types and measured wingspans, they missed the one specification that would redefine strategic bombing. The Lancaster's bomb bay ran unobstructed for 33 feet through the aircraft's centre section. No structural beams, no fuel tanks, no intrusive supporting framework. Just open volume waiting to be filled with tonnage German engineers thought physically impossible to carry. The story behind this unobstructed bomb bay begins with one of the most spectacular failures in British aviation history. In July 1936, the Air Ministry issued specification P1336, calling for a twin-engine medium bomber capable of carrying 8,000 pounds of bombs over 2,000 miles. The logic seemed sound. 2 engines meant lower production costs, less fuel consumption, and easier maintenance than 4-engine designs. Avro Aircraft's chief designer Roy Chadwick responded with the Type 679, later christened the Manchester. It looked brilliant on paper. The Manchester first flew on 25th of July 1939, and problems emerged immediately. Chadwick had been forced to use the Rolls-Royce Vulture engine, a 24-cylinder X-configuration beast that produced 1,760 horsepower. On paper, 2 Vultures could match the power of 4 smaller engines. In reality, the Vulture was an absolute disaster. The engine was essentially 2 Rolls-Royce Peregrine V12 engines mounted on a common crankcase, and that crankcase couldn't handle the stress. Connecting rods failed, cylinders cracked, coolant systems leaked. The Vulture overheated in level flight and caught fire with disturbing regularity. Number 2, 107 Squadron received the first operational Manchesters in November 1940, and within months, the aircraft had established a reputation that terrified its own crews more than German defences. On the night of 24th of February 1941, Flight Lieutenant Sherwood's Manchester suffered engine failure 20 minutes after takeoff. He coaxed the dying bomber back across the North Sea on one engine, but 3 crew members bailed out over England, certain they were about to die. On 13th of April, another Manchester lost both engines over Germany. The entire crew was killed. By June 1941, Manchesters were being withdrawn from operations after barely 6 months of service. But here's where desperation sparked genius. Roy Chadwick refused to accept that his fundamental airframe design was flawed. The Manchester's fuselage was sound. The wing structure was solid. The enormous bomb bay, designed to accommodate 8,000 pounds, was exactly what Bomber Command needed. The only problem was those cursed Vulture engines. So Chadwick did something brilliantly simple. He threw the Vultures in the bin and started again. The solution required extending the wingspan from 80 feet to 102 feet and mounting 4 Rolls-Royce Merlin engines instead of 2 Vultures. The Merlin was already powering Spitfires and Hurricanes with legendary reliability. Each Merlin 10 produced 1,280 horsepower, less than a Vulture individually, but 4 Merlins together delivered over 5,000 horsepower with none of the catastrophic failure modes. Chadwick's team worked with ferocious speed through late 1940 and early 1941, redesigning wing spars, recalculating weight distribution, and reworking fuel systems. The first Lancaster prototype, converted from a Manchester airframe, flew on 9th of January 1941 from Woodford Aerodrome. Test pilot Sam Brown reported the aircraft handled beautifully, with none of the Manchester's vicious tendencies. The engines purred. Controls responded smoothly. Most critically, that cavernous bomb bay remained completely intact. Chadwick had taken Britain's worst operational bomber and transformed it into something unprecedented. The Air Ministry, desperate for anything that actually worked, ordered immediate production. By Christmas 1941, the first Lancasters were arriving at operational squadrons. German intelligence documented this transition but interpreted it as Britain simply replacing one mediocre bomber with a slightly less mediocre variant, 4 engines instead of 2. That just meant more fuel consumption and maintenance headaches. They couldn't have been more catastrophically wrong. The Merlin engine sitting in each Lancaster nacelle was the same basic power plant that had saved Britain during the Battle of Britain, but what it accomplished in a heavy bomber was something else entirely. Each Merlin 20 or 22 produced 1,460 horsepower at takeoff, and these engines could maintain that output hour after hour without the dramatic failures that plagued German and even some American designs. Rolls-Royce had spent years perfecting the Merlin's liquid-cooled V12 configuration, and by 1942 it was arguably the most reliable aircraft engine in the world. Lancasters routinely flew 7-hour missions to Berlin and back, with all 4 Merlins running smoothly, whilst German bombers were still struggling with engine reliability over much shorter distances. But raw power was only part of the equation. What made the Lancaster truly revolutionary was how Chadwick's team had engineered the entire airframe around that unobstructed bomb bay. In every other heavy bomber of the era, German, American or British, the bomb bay was interrupted by structural supports, fuel tanks or equipment bays. The American B-17's bomb bay was divided into 4 separate sections by major structural beams. The Halifax had fuel tanks running through its bomb compartment. Even the Sterling, despite its size, could only accommodate bombs up to 2,000 pounds because of internal structural limitations. The Lancaster's bomb bay was different. Chadwick had designed the main wing spar to pass over the top of the bomb compartment rather than through it. This seemingly simple decision, moving a structural element a few feet higher, created 33 feet of completely unobstructed vertical and horizontal space. The bay was 9 feet wide and ran from just behind the cockpit, nearly to the tail section. You could stand in it, you could walk through it. More importantly, you could hang absolutely enormous bombs in it. When the Lancaster first entered service in early 1942, it could carry 14,000 pounds of standard bombs to targets in Germany, more than 3 times what German intelligence believed possible for an aircraft of its size. The typical load consisted of one 8,000-pound high-capacity bomb plus smaller weapons, or various combinations of 4,000-pound cookies and incendiaries. German analysts who interrogated captured Lancaster crews in mid-1942 initially dismissed their claims about bomb loads as either exaggeration or confusion about total squadron tonnage versus individual aircraft capacity. The physics seemed impossible to German engineers. An aircraft weighing 68,000 pounds, fully loaded, shouldn't be able to carry 14,000 pounds of that weight as bombs. That was more than 20% of maximum takeoff weight devoted to payload. German heavy bombers typically managed 8 to 10%. The Heinkel He-177, Germany's only operational 4-engine bomber, could carry 4,400 pounds maximum. Even that required reducing fuel load for shorter range missions. What German calculations missed was the Lancaster's extraordinary power-to-weight ratio and aerodynamic efficiency. 4 Merlins producing nearly 6,000 horsepower combined gave the Lancaster enough thrust to haul massive loads whilst maintaining operational altitude. The aircraft could cruise at 20,000 feet fully loaded, high enough to avoid the worst flak concentrations. Maximum speed at that altitude was 287 miles per hour, fast enough to make interception difficult for all but the most skilled night fighter pilots. The wing design contributed significantly to this performance. That 102-foot wingspan generated enormous lift, whilst the relatively clean aerodynamic profile minimized drag. Chadwick had obsessed over every detail that might reduce air resistance: flush riveting where possible, carefully faired engine nacelles, streamlined turrets. The result was an aircraft that could carry unconscionable amounts of ordnance over operationally useful distances whilst still handling like a fighter by heavy bomber standards. By late 1943, the Lancaster had already proven it could haul 14,000 pounds routinely, but Barnes-Wallis at Vickers Armstrongs was thinking bigger, much bigger. Wallis, the engineer who'd designed the bouncing bombs for the Dams raid, had become obsessed with earthquake bombs, weapons so massive they didn't need to hit targets directly. Instead, they'd penetrate deep underground and create shockwaves that would shatter foundations and collapse structures from below. His calculations showed these weapons needed to weigh at least 10 tons to achieve the required penetration depth and destructive effect. 10 tons, 22,000 pounds. The Air Ministry thought Wallace had lost his mind. No bomber in existence could carry such a weapon. The Lancaster's maximum bomb load was 14,000 pounds, and that was already stretching the aircraft to its limits. Asking it to carry an additional 8,000 pounds seemed not just ambitious, but physically impossible. The wings would snap. The undercarriage would collapse on takeoff. The engines couldn't generate enough power to maintain altitude. Every structural engineer who reviewed Wallace's proposal said the same thing. Fascinating concept, completely impractical delivery method. Wallace disagreed. He'd studied the Lancaster's design specifications obsessively and believed the airframe could handle far more stress than its official ratings suggested. The key was that cavernous bomb bay. A standard Lancaster could carry 14,000 pounds of multiple bombs distributed across the bay's length. But what if you hung a single weapon from the strongest structural points? What if you stripped out unnecessary equipment? Some of the armor plating, defensive guns from positions German night fighters rarely attacked from, even the bomb bay doors? What if you used the most powerful Merlin variants and accepted reduced fuel load for shorter range missions? Avro's engineers ran the calculations and reached a stunning conclusion. Yes, a modified Lancaster could theoretically carry 22,000 pounds. Not comfortably, not safely by peacetime standards, but it could be done. In May 1943, the Air Ministry authorised development of the Tallboy, Wallace's 12,000-pound earthquake bomb. This would serve as a stepping stone to prove the concept before attempting the even more ambitious Grand Slam. The first Tallboy was dropped on 8th of June 1944 by squadron leader Jock Calder, flying a modified Lancaster from number 617 Squadron. The target was the Saumur railway tunnel in France, critical to German reinforcement efforts after D-Day. The Tallboy punched through 70 feet of soil and rock before detonating, collapsing the tunnel so completely that it remained blocked for years after the war. German engineers examining the damage couldn't comprehend what weapon had caused such destruction. Their initial assessment suggested multiple bombs hitting simultaneously, because surely no single weapon could generate that much force. More Tallboy strikes followed through late 1944. On 15th of September, Lancasters carrying Tallboys attacked the Tirpitz in Kafjord, Norway. One bomb struck the battleship directly, punching clean through her armoured deck and blasting a hole in her bottom. The Tirpitz never sailed again. German naval intelligence requested urgent information about this new British superweapon, but Luftwaffe analysts had no answers. Their fundamental assumptions about Lancaster capabilities had been wrong from the start. Then came the Grand Slam. First dropped on 14th of March 1945 by squadron leader Charles Calder, yes, related to Jock, against the Bielefeld Viaduct in Germany. The 22,000-pound bomb was 35 feet long, with a hardened steel case designed to penetrate 100 feet underground before detonating. The Lancaster carrying it had been stripped of nearly everything non-essential. Mid-upper turret removed, bomb bay doors removed, nose turret replaced with a streamlined fairing, even some cockpit armour pulled out. The Grand Slam's devastating impact at Bielefeld showcased what the Lancaster could do at its absolute limits, but the aircraft's real strategic value lay in what it did night after night after night. From 3rd March 1942, when No. 44 Squadron conducted the first operational Lancaster raid against mine-laying operations in the Heligoland Bight, through to 25th of April 1945, when Lancasters hit Hitler's Berchtesgaden retreat. These bombers flew 156,192 sorties. To put that in perspective, every single night for over 3 years, an average of 143 Lancasters were airborne over enemy territory. The tonnage figures tell an even more remarkable story. Lancasters dropped 608,612 tons of bombs during the war, comprising 64% of all ordnance delivered by Royal Air Force Bomber Command. The Halifax, which served longer and equipped more squadrons at certain points, managed 227,610 tons. The Sterling, despite entering service first, delivered just 15,300 tons before being relegated to transport duties. The Lancaster didn't just outperform its contemporaries, it buried them in statistical irrelevance. These numbers represent an industrial-scale bombing campaign that German defences struggled to counter. Take the 1,000 bomber raids that began in May 1942. The first raid against Cologne on the night of 30th May involved 1,047 aircraft, but only 73 were Lancasters because production was just ramping up. Fast forward to March 1945, and raids involving 600 to 800 aircraft were routine, with Lancasters comprising 70 to 80% of the force. The aircraft had become so dominant that operational planning assumed Lancaster availability rather than questioning it. Reliability drove this operational supremacy. A Halifax crew could expect their aircraft to abort roughly 1 mission in 10 due to mechanical failure. Sterlings were worse. Lancasters aborted at roughly half that rate, meaning more aircraft reached targets and delivered ordnance. Squadron leader Leonard Cheshire, who commanded No. 617 Squadron and later No. 5 Group, noted that Lancasters consistently achieved serviceability rates above 80%, extraordinary for complex four-engine bombers operating under wartime conditions, with overworked ground crews and parts shortages. The human cost was staggering, but would have been far worse with inferior aircraft. 3,349 Lancasters were lost on operations, and another 2,340 were damaged beyond repair or lost in accidents. Of the 125,000 aircrew who served in Bomber Command during the war, 55,573 died, a 44% fatality rate. But Lancaster crews had marginally better survival odds than Halifax or Sterling crews, primarily because the aircraft could absorb more battle damage and still bring its crew home. Flight Lieutenant William Reed's experience on 3rd November 1943 exemplifies the Lancaster's toughness. His aircraft was attacked by a Messerschmitt Bf 110 over the Dutch coast while heading to Düsseldorf. Cannon fire shattered the windscreen, wounded Reed in multiple places, and knocked out the compass and communications. A Focke-Wulf 190 attacked minutes later, killing the navigator and wounding more crew. Reed flew on, dropped his bombs on target and brought the crippled Lancaster back across the North Sea to crash land at Shipdham. He received the Victoria Cross, but dozens of Lancaster pilots performed similar feats with less recognition. By early 1945, Bomber Command could dispatch 700 Lancasters in a single night, 700 aircraft each carrying 14,000 pounds of bombs. That's 9.8 million pounds of ordnance in one raid. German industry couldn't sustain that kind of systematic destruction. Cities couldn't be rebuilt faster than they were being demolished. The Boeing B-17 Flying Fortress remains one of the most celebrated aircraft in American military history, but its combat performance revealed fundamental design trade-offs that contrasted sharply with Lancaster doctrine. When the 8th Air Force began daylight operations over Europe in August 1942, B-17s typically carried 4,000 to 5,000 pounds of bombs on missions into Germany. Maximum theoretical bomb load was supposedly 12,800 pounds, but that figure only applied to short-range missions with minimal fuel and no defensive ammunition, conditions that never existed in actual combat over Europe. The disparity wasn't accidental. American bombing doctrine emphasized daylight precision attacks on specific industrial targets rather than night area bombing of cities. To survive in daylight against German fighters, the B-17 bristled with defensive guns, 13 50 caliber machine guns, by the time the G model entered service. All that defensive armament added weight, the ammunition added more weight. The armor plating protecting gunners and critical systems added even more. Flying in tight defensive formations for mutual protection meant aircraft couldn't carry external stores on wing racks. Every design decision prioritized survival over payload. The mathematics were brutal. A B-17G weighed 65,000 pounds, maximum takeoff weight. Defensive armament, ammunition, and additional armor consumed roughly 5,000 pounds. Fuel for a deep penetration mission to targets like Schweinfurt or Regensburg required another 7,000 pounds. The 10-man crew, their equipment, and survival gear added another 2,000 pounds. By the time you accounted for all the systems needed to fight through German defences in daylight, approximately 4,000 to 6,000 pounds remained for bombs, roughly one-third what a Lancaster carried routinely at night. The 17th of August 1943 Schweinfurt-Regensburg mission illustrated these limitations starkly. 230 B-17s attacked ball-bearing factories, each carrying approximately 4,000 pounds of bombs. The raid delivered roughly 920,000 pounds of ordnance total, but lost 60 aircraft with their crews. That same tonnage represented what about 66 Lancasters could carry in a single night raid, and typical Lancaster loss rates in 1943 averaged around 4%, meaning roughly 3 aircraft lost for the same destructive effect. The Americans weren't blind to this disparity. Lieutenant General Ira Eaker, commanding the 8th Air Force, repeatedly requested modifications that would increase B-17 bomb capacity, but any attempt to carry more ordnance meant reducing fuel, ammunition, or defensive guns, each of which meant higher losses to German fighters. The B-17 was trapped in a tactical catch, 22. It needed heavy defensive armament to survive daylight operations, but that armament prevented it from carrying the bomb loads necessary to justify the horrific loss rates. The arrival of long-range escort fighters partially solved this dilemma. Once P-51 Mustangs could accompany bombers all the way to targets and back from early 1944 onwards, B-17s needed less defensive armament and could theoretically carry more bombs. Some units experimented with removing guns and adding bombs, but ingrained operational procedures and the aircraft's structural limitations meant typical loads still hovered around 6,000 pounds maximum, less than half what Lancasters carried on equivalent missions. Allied planners adapted to these realities by assigning complementary roles. The Americans would bomb precision targets by day, when visibility allowed accurate attacks on specific factories, marshalling yards, and oil facilities. The British would bomb broader target areas by night, carrying enough tonnage to overwhelm German fire defences and civil defence services. This wasn't cooperation born from strategic brilliance, but rather practical accommodation of fundamentally different bomber capabilities. The Lancaster's payload advantage enabled missions that German defensive planning hadn't even considered possible. Take Operation Chastise, the Dams raid, launched on the night of 16th of May 1943. Wing Commander Guy Gibson led 19 specially modified Lancasters from No. 617 Squadron to attack the Murner, Eder and Sorpe dams in the Ruhr Valley using Barnes-Wallis's rotating cylindrical bombs. Each bomb weighed 9,250 pounds and had to be dropped from exactly 60 feet altitude at precisely 232 miles per hour, spinning backwards at 500 revolutions per minute. The modifications required to make this work were extraordinary. Engineers removed the bomb bay doors entirely and installed caliper arms to hold the cylindrical weapon crossways beneath the fuselage. A hydraulic motor spun the bomb up to speed before release. V-shaped spotlights mounted under the nose and tail converged at exactly 60 feet altitude, giving pilots a precise height reference over water at night. The weapon itself bounced across the reservoir surface like a skipping stone, struck the dam wall, sank while maintaining backspin, then detonated against the dam face at a preset depth of 30 feet. German defences at the Murner included flak positions, torpedo nets, and barrage balloons, but no one had planned for aircraft attacking at wave-top height or weapons that bounced across water. The first bomb dropped by Gibson reached the Murner at 12:28 a.m. on 17th of May. The Eder Dam, undefended because its remote location was considered protection enough, was breached at 1:52 a.m. The resulting floods destroyed power stations, factories, and infrastructure across the Ruhr industrial region. German engineers examining the damage couldn't initially determine what weapon had caused the breaches. The impact patterns and damage characteristics matched no known bomb or torpedo. The Tirpitz represented another seemingly impossible target. Germany's largest battleship spent most of the war hiding in Norwegian fjords, protected by smoke screens, anti-aircraft batteries, torpedo nets, and fighter cover. Multiple attempts to sink her with conventional bombing had failed. Then Lancasters carrying 12,000-pound tallboys entered the equation. The first successful attack came on 15th of September 1944, when 28 Lancasters from numbers 9 and 617 squadrons attacked Kharfjord. Flying from Yagodnik in northern Russia, after an 11-hour flight from Scotland, they dropped tallboys from 14,000 feet. One tallboy struck Tirpitz directly, punching through her armoured deck and blasting through the ship's bottom. German Naval Command moved the crippled battleship to Tromsø for repairs, but she never sailed again. On 12th of November 1944, 32 Lancasters attacked her anchorage with tallboys and Grand Slams. 3 direct hits capsized the ship, killing nearly 1,000 sailors. A battleship that had survived torpedo attacks, commando raids, and conventional bombing was obliterated by bombs dropped from 3 miles up. The Bielefeld Viaduct raid on 14th of March 1945 showcased precision that German defensive doctrine said was impossible at night. The viaduct's arches were heavily defended and considered indestructible by conventional bombing. Squadron leader Charles Calder's Grand Slam hit 100 yards from the viaduct, penetrated 60 feet underground, and detonated. The shockwave collapsed 100 yards of the structure. Follow-up raids with tallboys destroyed additional sections. The viaduct, supposedly impervious to bombing, ceased to exist. These specialized missions succeeded because the Lancaster could carry weapons no other operational bomber could lift while maintaining the range and altitude necessary to reach targets deep in occupied Europe. German defensive planning had evolved to counter mass raids dropping conventional bombs. No one had prepared for individual aircraft delivering earthquake bombs that didn't need to hit targets directly. By spring 1944, Luftwaffe night fighter pilot Major Heinz Wolfgang Schnaufer had accumulated 74 confirmed kills, making him one of Germany's deadliest night fighter aces. His combat reports revealed a striking pattern. Whenever he encountered a mixed bomber stream containing Lancasters, Halifaxes, and Stirlings, he prioritized Lancasters. Not because they were easier targets, quite the opposite. Lancasters were harder to shoot down than other British bombers, more maneuverable, and their crews fought back viciously. Schnaufer targeted them because intelligence briefs finally made clear what operational reality had been screaming for 2 years. Lancasters were delivering the tonnage that was systematically demolishing German industrial capacity. This represented a complete reversal from 1942's dismissive assessments. Interrogation reports from captured Lancaster crews in 1944 showed German intelligence officers asking extraordinarily detailed questions about bomb loads, modification procedures, and operational capabilities. They needed to understand how a bomber they'd catalogued as conventional was routinely carrying payloads that exceeded theoretical maximums for aircraft twice its size. Some interrogators openly expressed disbelief when aircrew described Grand Slam and tallboy operations, assuming prisoners were providing disinformation under questioning. Oberst Harjo Hermann, architect of the Weald-Sau freelance night fighting tactics, issued directive modifications in June 1944, specifically addressing Lancaster formations. German controllers were instructed to vector night fighters toward Lancaster heavy streams rather than mixed formations. The reasoning was grimly practical. Shooting down 3 Halifaxes carrying 9,000 pounds of bombs combined did less to reduce damage than shooting down 2 Lancasters carrying 28,000 pounds together. Mathematics and desperation drove German tactical evolution. The problem was that recognizing the Lancaster's supremacy didn't provide solutions for stopping it. German night fighters, primarily Messerschmitt Bf-110s and Junkers Ju-88s, were optimized for attacks from below and behind, targeting bomber fuel tanks and bomb bays with upward-firing Schrager music cannons. This worked brilliantly against Halifaxes and Stirlings, whose fuel systems were vulnerable to upward fire. Lancasters, with their fuel tanks positioned differently and that cavernous bomb bay often filled with a single large weapon rather than multiple smaller bombs, proved far more resistant to these attacks. Major Rudolf Schonert, commanding Nachtjagdgeschwader 100, reported in August 1944 that his unit's kill rate against Lancasters was roughly 30% lower than against equivalent numbers of other heavy bombers. The Lancaster's rear turret, equipped with 4 303 caliber Browning machine guns, could track targets effectively and put enough rounds downrange to force German fighters to break off attacks. Flight engineers in the Astrodome could spot fighters approaching from above, giving gunners precious seconds to respond. The combination of structural resilience and effective defensive fire made Lancaster kills costly for German pilots. By autumn 1944, Luftwaffe night fighter losses were approaching unsustainable levels. Bomber Command's tactical improvements, including bomber support squadrons flying Mosquitoes to hunt German fighters, improved electronic countermeasures, and better routing, meant German interceptors were dying faster than replacement pilots could be trained. Schnaufer himself noted in his diary that by October 1944 he was regularly encountering streams of 400 to 600 Lancasters with perhaps 30 German fighters available to intercept them. The mathematics of attrition had shifted decisively against Germany. The Luftwaffe's belated recognition of Lancaster capabilities came too late to matter strategically. Yes, German pilots had finally learned to prioritize the bombers doing the most damage. Yes, tactics evolved to address Lancaster-specific vulnerabilities, but by the time these countermeasures materialized, Germany's industrial base was already shattered, fuel production had collapsed, and pilot training programs couldn't replace losses. The Lancaster's combat record forced every major air force to reconsider fundamental assumptions about heavy bomber design. Before 1945, conventional wisdom held that strategic bombers needed extensive defensive armament to survive enemy fighters, even if that armament drastically reduced payload capacity. The Lancaster demonstrated that high payload delivered consistently over years of operations mattered far more than theoretical survivability in individual engagements. This wasn't immediately obvious to military planners, but the statistical evidence was overwhelming. One Lancaster carrying 14,000 pounds of bombs accomplished more strategic destruction than two B-17s carrying 4,000 pounds each, even accounting for different loss rates. The Americans absorbed this lesson while designing the Boeing B-29 Superfortress. Although B-29 development began before the Lancaster's capabilities became clear, late war modifications increasingly emphasized payload over defensive armament. The B-29 could carry 20,000 pounds of bombs, approaching Lancaster performance, but only after engineers accepted reduced defensive systems and relied more heavily on altitude and speed for protection. Post-war B-29 variants stripped out even more guns, acknowledging what the Lancaster had proven. In strategic bombing, tonnage on target matters more than individual aircraft survival rates. Soviet aviation design bureaus studied captured German intelligence reports on Lancaster operations with intense interest. The Tupolev Design Bureau's Tu-4 bomber, which first flew in May 1947, showed clear influences from Lancaster principles despite superficially resembling the B-29. Soviet designers prioritized an enormous unobstructed bomb bay capable of carrying everything from conventional bombs to early nuclear weapons. The Tu-4's maximum bomb load reached 22,000 pounds, exactly matching the Lancaster's Grand Slam capability. This wasn't coincidence. It was Soviet planners recognizing that payload capacity defined strategic bombing effectiveness. The British themselves took Lancaster lessons forward with the Avro Lincoln and later the V-bomber force. The Lincoln was essentially a stretched, more powerful Lancaster optimized around even larger bomb bays. When Britain developed its nuclear deterrent in the 1950s, all three V-bombers, the Valiant, Victor, and Vulcan, featured massive unobstructed bomb bays as their central design element. The Vulcan could carry 21,000 pounds conventionally, or a single nuclear weapon. Direct conceptual descendants of Lancaster's philosophy, that bomb bay volume and payload capacity trumped almost every other consideration. American Cold War strategic bomber development followed similar trajectories. The Convair B-36, designed in the mid-1940s, could carry 72,000 pounds of bombs, an absurd figure that only made sense in a world where the Lancaster had demonstrated that massive payloads were operationally viable. The Boeing B-52, which entered service in 1955 and remains operational today, was designed around a payload capacity of 70,000 pounds. Both aircraft sacrificed defensive armament, relied on altitude and electronic countermeasures for protection, and organized their entire structure around delivering maximum tonnage on target. The doctrinal shift was equally profound. Pre-Lancaster strategic bombing theory emphasized precision attacks on specific targets using bombers that could fight their way through enemy defenses. Post-Lancaster doctrine accepted that strategic bombing meant overwhelming enemy defenses through sheer tonnage, targeting industrial regions rather than individual factories, and designing bombers primarily as payload delivery systems rather than flying fortresses. This wasn't morally comfortable doctrine. It led directly to concepts like mutually assured destruction, but it reflected what combat experience had proven. Winning strategic bombing campaigns required delivering more ordnance than the enemy could absorb, not flying the most heavily armed individual aircraft. The Lancaster's influence extended beyond specific aircraft designs to reshape how military planners calculated strategic bombing effectiveness. Payload-to-range ratios became the primary metric for evaluating heavy bombers. Defensive armament became secondary. The Lancaster hadn't just been an excellent bomber, it had redefined what excellence meant.